Hi everyone, my name is Shubhartak Sangharsh, a Master of AI and Machine Learning student at Adelaide University. Today, I'm presenting my preliminary dataset analysis for my capstone project, which is titled as Learning Action Conditional World Models for Autonomous Navigation in Robotic Systems. It is supervised by Professor Peng and co-supervised by Dr. Bing Yan. Today, I will cover four things. First, the motivation and research problem, where I will explain the background of robotic autonomous navigation, the gaps in existing methods, and the project's aims. Second, the dataset description and understanding. Third, the data analysis with preliminary findings. And fourth, the next steps and areas where I'm seeking feedback. Let me get into it. All right, so this slide covers the motivation and research problem. The research background is a robotic autonomous navigation, which is a core challenge in AI and robotics, enabling robots to move safely and efficiently in an unknown dynamic environments without human guidance, as shown in the figure on the right. Existing approaches have two critical limitations. First, traditional map-based planners like SLAM and A-star break down when no prior map exists or when environment change dynamically. Second, reactive deep reinforcement learning policies treats every observation in an isolation with no look ahead, making them vulnerable to get stuck in something called local optima in a complex environments. World models offers a fix. A compact neural network learns how the environment evolves in a response to actions, letting the robot mentally simulate candidate futures before acting. On the right, you can see our gazebo simulation. The blue dot is the robot, the star is the goal, and the orange lines are the lidar scans. Now, the, basically there are three research questions which guides the project. Research question 1 asks whether a lightweight action conditional world model can accurately predict future robot states measured by SSIM and MSE mean square error. Research question 2 asks whether combining that world model with a CEM planner improves navigation success rate and collision avoidance compared to a PPO reactive baseline. And research question 3 looks at which architectural choice matters the most, including RSSM versus casual transformers, and basically image space versus feature space prediction, and planning horizon length. Building on these questions, the project has three core aims. First, to build a lightweight action conditional RSSM world model for robotic navigation. Second, to integrate it with a CEM planner and demonstrate it to outperform the reactive deep RL baseline. And third, to conduct the ablation studies to identify the optimal architectural choices. Now, let's come to methodology. The methodology has three phases. Phase 1. Set up a Gazebo and ROS2 simulation with a Turtlebot 3 robot across 5 procedure-generated maps and collect HDF5 trajectory data. Phase 2. Train an RSSM world model or a GRU with a casual self-attention, a CNN image encoder and image decoder, and a reward MLP. Phase 3. Deploy a CEM planner that samples action sequences, roll them through the world model in the latent space, and pick up the best one. You can see the full architectural design below, right? So let's move on to dataset and dataset overview. Because this is a model-based RL project, there is no public dataset to download the agent. So basically, the agent generates its own data by interacting with Gazebo. I have two sources. First, an exploration dataset of 512,000 transitions collected from a random policy across all 5 maps used to train the world model dynamics. Now, the second one is 105,000 transition from a pre-trained PPO agent, which provides higher quality goal-directed trajectories for fine-tuning the reward predictor, combining 617,000 transitions stored in HDF5 with an 80-10-10 train validation test split. Moving on Each transition contains two observation modalities, a 64 by 64 pixel depth image from a front-facing camera and a 2D laser scan vector. You can see sample depth sequence on the left for environment. The corridor shows strong edge structure, open spaces are much brighter, and cluttered environments have scattered obstacle patches. Actions are continuously velocity, comma, linear velocity from 0 to 0.26 meter per second, and angular velocity up to 1.82 radians per second encoded as a two-dimensional float vector with no discretion. Moving on, the pipeline runs left to right. So basically, the Gazebo hosts the 5 maps. Turtlebot 3 runs the depth camera and lidar on ROS2. A policy executes a subscriber node capture each transition tuple, and everything is written to HDF5 file split at the episode level. The HDF file tree at the bottom shows three with splits, each holding observation, actions, reward, and done flags. One issue I encountered running a Gazebo and PPO training simultaneously caused GPU memory conflicts. I resolved it by decoupling the collection CPU only from training GPU only. 4 processing steps before training. First, integrity checks. All 617,000 transition verified for NaN values and out-of-range readings. 0 corrupted samples were found. Second, normalization depth images were normalized per channel. Laser scans scaled to -1 to 1. Third, the action encoding kept as a continuous flow throughput. Fourth, the episode level train validation test splits stratified across all 5 environments to prevent data leakage. Moving on. Now for the data analysis, looking at the mean episode, which is the data analysis, the important part. So basically the mean episode reward by environment, open space is highest at 81.2 and cluttered at lowest 44.8. When I dug into the success rates, the PPO agent only completed navigation 12% of the time in the cluttered environment versus 74% average across the others. The episode length chart tells the same story. The cluttered environment averaged 267 steps, nearly double the 145 of open space. The robot is spending far more time struggling to find the path, which is exactly where the world model with look-ahead planning should add value. Now, coming for data analysis, I also analyze action distributions. The exploration dataset is close to uniform across all 6 angular velocity bins. Good diversity for world model training. The PPO dataset is skewed toward forward position motion as expected from goal-seeking agent. Linear velocity checks confirm 85% of exploration transition uses velocity above 0.1 meter per second. So the robot was genuinely basically rather than spinning in place. No gaps in action coverage that would limit the CEM planner. Now, I also check out the trajectory heat maps, which confirms that the dataset are complementary. Exploration provides broad coverage, while PPO focus near goal regions. Overall, the dataset quality is high, with consistent depth observation and stable temporal sequences. Importantly, the outcome distribution shows a balanced mix of goal reaching, collision, and timeouts. This is basically significant because it ensures the reward predictor learns from the diverse outcome, which is critical for stable and effective world model training. Now, the most important findings from the analysis is the class imbalance. The cluttered environment has 12% PPO success rate versus 74% everywhere else, which you can see clearly the orange bar here. Yeah, this means that the task-specific dataset is heavily underrepresented for cluttered scenarios, the exact scenarios where the model needs the strongest reward prediction signal. The mitigation plan has 4 parts. Oversample cluttered episodes during the reward predictor fine-tuning, collect additional random policy rollouts in that environment, monitor reward prediction MSC per environment separately during training. For the next weeks, I have figured out specifically value the feedback on 3 points. The oversampling strategy for the cluttered dataset imbalance, whether a 10-step CEM horizon is appropriate for my environment scale, and whether the RSSM versus casual transformation ablation is worth the time given my deadline. So basically, to summarize, the problem is that the reactive deep RL forward planning, it basically lacks the forward planning. The solution is an RSSM world model with a CEM planner in Gazebo. The dataset is 617,000 transition across all the environments. The key finding is the cluttered environment imbalance with the mitigation plan in place. The next steps are training, integration, and ablation. Thank you for watching. I welcome your questions or feedback. Thank you so much.